In May of 2026, researchers published a study that exposed a fundamental vulnerability in the human brain. They strapped EEG brain mapping caps onto 27 people and had them read text generated by artificial intelligence. Some sentences were true. Others were highly fluent, contextually plausible lies. The brainwaves revealed something terrifying. When humans read fluent grammatical nonsense written by machines, our brains do not trigger the typical error detection signals we usually produce when we hear a human lie. We are neurologically blind to fluent falsehoods. Because the grammar is perfect and the tone is confident, our brains process synthetic fiction as absolute fact. This means we cannot rely on human intuition to police artificial intelligence. As these models are deployed in medicine, law, and search engines, the tech industry has had to accept a harsh truth. We cannot make these models stop lying. Instead, we have to build complex software cages to catch the lies before they ever reach our screens. For years, the public was told that if we just made these models bigger, trained them on more data, and gave them more computing power, their errors would simply evaporate. This was the gospel of the scaling laws. But by 2026, that dream died. Brute force pre-training has hit a hard ceiling. The internet has run out of high-quality, human-written data. Copyright lawsuits have locked up premium archives, and models trained on their own synthetic outputs are starting to degrade. The industry is facing a quiet crisis. The underlying engines are not getting fundamentally smarter or more truthful. They are still probabilistic prediction machines. They do not know what a fact is. They only know what word is most likely to follow the previous one. To build tools that doctors and engineers can actually use, the focus has shifted entirely away from training larger models. The real breakthrough of 2026 is not a smarter brain, but a highly sophisticated set of external filters. To understand how modern AI products actually work, you have to picture the raw model not as an intelligent assistant, but as a high-pressure geothermal geyser. The geyser is incredibly powerful, but it is also completely chaotic. It spews a volatile mixture of pure energy, boiling water, and toxic sulfur. You cannot convince the geyser to only release clean, drinkable water. It is simply behaving according to the laws of pressure. If you want to use that geyser to power a city, you do not try to change the earth underneath it. Instead, you build a massive, complex system of steel pipes, pressure regulators, and filtration valves around it. In this system, the raw language model is just the geyser. The product we actually interact with is the plumbing. Every accurate answer you receive from an AI is not a sign that the model has suddenly become wise. It is the result of a chaotic torrent of probabilities being forced through a strict, multi-layered pipeline of software engineering. This plumbing is most visible in how we search the web. We have transitioned away from traditional search engines toward what computer scientists call GenIR, or generative information retrieval. In the old days of the internet, a search engine was a passive librarian. You asked a question, and it handed you a list of books where the answer might live. It was up to you to read the pages and verify the facts. GenIR changes this relationship entirely. Instead of handing you the sources, the system reads the web pages for you, extracts the relevant pieces, and synthesizes a custom response in real time. This is incredibly convenient, but it introduces a massive hazard. The moment a system synthesizes information, it is no longer just retrieving data, it is generating new sentences. If the model connects two unrelated facts from two different articles, it creates a synthetic lie that looks completely authentic. To stop this, engineers have had to build dynamic real-time checking systems that act as an invisible editor, monitoring the generation word by word. In high-stakes fields like medicine, a single hallucination can be fatal. If an AI summarizing a doctor-patient dialogue invents a symptom or misrepresents a dosage, the consequences are catastrophic. To deploy these systems in hospitals, engineers use specialized diagnostic filters, such as the leave-in-out method, documented in clinical AI research. This system does not trust the model's output. Instead, it systematically tests the generation by isolating facts. The diagnostic software takes the raw medical summary and deliberately removes specific pieces of input data, then runs the model again. If the model still tries to assert a specific medical fact, even when the supporting clinical evidence has been removed from its prompt, the system flags it as a structural hallucination. By constantly probing the model with these micro-tests behind the scenes, the software can pinpoint exactly where the model is relying on its training memory rather than the actual patient record. It is a digital lie detector test that runs dozens of times in the span of a single second. The frontier of this engineering, detailed in cutting-edge 2026 preprints, is a process called phase-wise self-rewarding at inference time. Historically, companies tried to fix AI errors by training them on human feedback. But this training is static. Once the model is released, its internal weights are frozen, and it can still make mistakes when faced with new situations. Phase-wise self-rewarding changes this by turning the model into its own real-time critic. As the AI generates a sentence, the software stops it at critical checkpoints, or phases. Before the next words are displayed to the user, the system spins up a secondary evaluation loop. It asks itself, is this claim supported by the verified documents in my context window? The model literally scores its own progress in milliseconds. If the score falls below a certain threshold, the system discards the draft sentence and forces the model to choose an alternative path. The AI you interact with is not just thinking ahead. It is constantly rewriting its own work in the brief pause between the characters flickering onto your screen. But this elaborate scaffolding comes with a massive cost. The industry calls it the alignment tax, and it is paid in three currencies: speed, compute, and money. When you ask a raw, unmonitored model a question, it responds instantly. But when you wrap that model in real-time self-rewards, diagnostic filters, and retrieval verification steps, the system has to perform 5 to 10 times more work for every single prompt. This is why many premium AI tools feel slower today than they did during the early days of the AI hype. It is not because the hardware is worse. It is because the software is performing an incredibly heavy dance of verification behind the scenes. This verification requires massive amounts of extra processing power, which translates directly into higher energy bills for data centers and higher subscription fees for users. We have reached a point where the cost of generating a fact is no longer about the size of the model, but the complexity of the security guards we hire to watch it. When we use modern AI products and receive flawless, accurate answers, it is easy to believe we are interacting with a machine that has achieved a deep, structured understanding of our world. But that is the ultimate illusion. What we are actually witnessing is a highly choreographed theatrical performance. The raw machine is still the same wild, untamed geyser of probabilities it has always been, fundamentally incapable of distinguishing truth from fiction. The accuracy we see is not an inherent quality of the artificial intelligence. It is a triumph of system engineering. We have not cured the hallucination. We have simply built a prison of code so precise and so fast that the lies are caught and destroyed before our eyes ever have the chance to believe them.